We're surrounded by software. It's everywhere. Our phones, our cars, our banks, you name it. But here's the crazy thing. What if this entire digital world is built on a foundation that's actually kind of fragile? For every amazing thing software can do, there's always a risk that it can break in some really spectacular and sometimes pretty dangerous ways.
So that brings up the big question, right? Why does our software keep breaking all the time? Is it just bad luck, some random glitch in the system, or is there something way more deliberate going on here? Let's dig in.
Okay, so to get to the bottom of this, first we have to get one thing straight. Not all software flaws are the same. See, we're not just talking about your typical accidental bugs here. We're talking about vulnerabilities. Think of them like tiny cracks in a fortress wall, just sitting there, waiting for someone with bad intentions to find them.
And this is a really, really important distinction to make. On one hand, you've got software quality. That's all about making sure the program doesn't crash during normal, everyday use. It's about developers finding and squashing those random bugs. But software security, that's a whole different ballgame. That's about defending against a smart, motivated attacker who is actively hunting for that one specific flaw they can use to break in. They don't care about the 99% of your app that works perfectly. No, they are laser focused on that tiny 1% that doesn't.
So how in the world do they find that 1%? Well, for starters, an attacker is never, ever going to use your app the way you're supposed to. While a normal quality tester checks if everything works as planned, an attacker does the opposite. They throw absolute curveballs at it, inputs that are way too long or full of weird symbols or just plain nonsense. They're literally trying to make it crash, to provoke some weird error that they can then turn into a weapon.
So how do we possibly fight back against that? This is where we introduce the hero of our story, defensive programming. You can basically think of it as being professionally paranoid. The whole idea is to build software from the ground up, assuming that it's already under attack. It's designed to constantly check everything, and if something does go wrong, to fail safely instead of just handing the keys over to an attacker.
All right, let's see what this looks like in the real world. I want you to imagine a program as like a fortress. What's the most vulnerable spot? It's always the gates, right? The places where things from the outside world have to come in. Well, in software, those gates are the program's inputs.
And if this fortress has one golden rule, one law that you absolutely cannot break, it's this: never ever trust input. I don't care if it's coming from a user typing on a keyboard, a file, or another computer on the network. You have to treat all of it as if it could be hostile. Don't assume it's the right format, the right length, or that it isn't hiding something nasty.
Because if you do break that rule, you get something like an injection attack. This is one of the most common and devastating vulnerabilities out there. And it happens when a program gets tricked into running data that it thought was just harmless information. Okay, let's break this down. Let's say a program asks you for your username. A normal person types in Bob. Simple enough. But an attacker, they type in Bob, but then they add a little something extra, like a semicolon, and then a command like delete all files. If the program isn't built defensively, it doesn't just see the name Bob, it sees that semicolon and goes, oh, a new command? You got it, boss.
And just like that, the consequences can be, well, catastrophic. That simple little input box becomes a wide open backdoor. This isn't some theoretical thing either. This is exactly how so many of those huge data breaches you read about actually happen. A single cleverly crafted input gets twisted into a command to delete an entire database, all because the program was too trusting.
Okay, so we've guarded the gates, but what happens if the danger comes from within? It's not just about what comes into the fortress. Vulnerabilities can be lurking deep inside the program's own logic, in the very rules it uses to operate.
One of the most fundamental rules for internal security is what's called the principle of least privilege. It's a really simple idea, but it is incredibly powerful. All it means is that any part of a system should only have the bare minimum permissions it needs to do its job, and nothing more. The valet key is the perfect way to think about this. When you give your car to a valet, you give them a key that can only start the car and lock the doors. You don't give them the key to your house, your office, and your bank vault. Why? Because you want to limit the potential damage if something goes wrong. It's the exact same with software. That's what this principle does. It contains the blast radius of an attack. All right, another classic internal flaw is something called a race condition. This is what happens when the final outcome of something depends on the totally random timing of different events. Just imagine two different parts of a program trying to update your bank balance at the exact same microsecond. Who gets to go first? Who wins? If the code isn't ready to handle that conflict, the result is just chaos. So, on the left, you've got this nice orderly process. Task A finishes, then task B starts. It's clean, it's predictable, it's safe. But on the right, that's a race condition. It's pure chaos. Both tasks are stomping on each other, trying to use the same resource at the same time. This leads to corrupted data and totally bizarre behavior that, you guessed it, can often be exploited by an attacker.
Okay, for our last section, we're going to talk about something that might sound a little strange at first. We've talked about dangers coming into the program and mistakes happening inside the program. But what if the actual output of the program, the stuff it sends back out to you, could be turned into a weapon?
Well, that is the entire idea behind a cross-site scripting attack, or XSS for short. It's an incredibly clever attack where a hacker uses a website you trust as a delivery system for their malicious code. And what's so sneaky about this is that the hacker isn't really attacking the website itself. Nope, they're using the website to attack you, the user.
Here's a classic example, a website guestbook. An attacker leaves a comment, but hidden inside that comment is a malicious script. The website, not knowing any better, just saves the comment to its database. Now, when the next person comes along to read the comments, their web browser sees that script and just runs it. And that script can do all sorts of nasty things, like steal their login cookie or send them to a phishing site.
And the reason this whole thing works is because it exploits trust. Your browser is built to trust the code that comes from the websites you visit. So when that malicious script is delivered by a trusted website, your browser just lets its guard down. The website basically becomes an accomplice. It doesn't even know it, in an attack against its very own users.
So after all that, what's the big takeaway here? It really all boils down to this thing we're calling the defender's mindset. It's a philosophy. Never trust input. Validate absolutely all of your assumptions. Use the least privilege possible. Make sure you fail safely. And always, always sanitize your output. It's not a checklist you finished once, it's a constant state of vigilance.
And that leaves us with one last, kind of sobering thought. Every single time you open an app, you visit a website, you use any piece of technology, you are placing your trust in the software that runs it. The real question you have to ask yourself is, how much of that code was actually built with this kind of paranoid defender's mindset?